Hi, and thank you very much to the conveners of this session on the scientific results of the International Ocean Discovery Programme, A Decade of Success, for inviting us to do the keynote talk in this session. So today I'm going to be co-presenting some work that we have on a submarine mineral system from Expedition 331 and some exciting new results on chromium and strontium isotopes. So this study has been completely funded by an ANZIC legacy grant. So a little bit about the background and the rationale to this project. Active hydrothermal systems in the submarine realm are reasonably easy to see. We've got an example of one up there up on the screen, smoking away. They're incredibly hard to find in the rock record, and these are some of our biggest repositories of elements such as copper, lead, and zinc. So what is it that we need to look for in the rock record to find these things? And how big could we potentially have as a footprint to find one of these submarine hydrothermal systems? So it's really useful to look at active examples, but this is really only possible through programs like IODP that give us access to the seafloor. A bit of background on our submarine hydrothermal systems. They occur in two main tectonic settings. In figure A, you see the spreading ridges, which generally tend to be associated with basaltic volcanism, but we can also get them in arc and back arc areas labeled as 2 and 3 on figure B there. And these tend to be more associated with intermediate to sometimes quite felsic rock types. There's some important inputs in these systems. Obviously, we need a heat source, which comes from the magma. We need a fluid source, and this can be magmatic or from the seawater. And we need that input of metals, and this can be from a magmatic source or from the host rocks that the fluids and the magmas are coming through. And there's a beautiful example from the literature of one on the slide there, showing a copper-rich chalcopyrite core, and then a zinc and lead-rich sphalerite outer to the chimney sample there. So there's a very complex interplay between magmatic and seawater dominated regimes. So background onto the area that we chose our samples from. Our samples are from IODP leg 193, which was an expedition in 2010. They're from the back arc region of the Japan intraoceanic arc, which you can see in the figure there. This is a back arc area where we have active extension going on, but there's also subduction of a ridge. And this has caused quite high heat flow and quite a predominance of hydrothermal fields. The host rocks in this area are bimodal volcanics, so although there are some basalts, there's also a lot of felsic rocks in this area, so dacite to rhyolites. The main aim of this expedition, which was called the Deep Hot Biosphere Expedition, was to actually look for active, diverse biosphere underneath the subsurface. But it's obviously also given us access to some wonderful samples which show these hydrothermal fields which are currently active. So the field that we're going to be looking at is the Iheya North hydrothermal field in the middle Okinawa Trough. Zooming in a little bit more on that area, if you see on the right, that's a bathymetric image. There were 5 main drill sites from this expedition, and they drilled it into the foot of the North Big Chimney, which is site C0016, which I'll refer to as site 16. There was a site of recent activity, which is site 13, which was just about 100 meters away from this big chimney. There's a lower temperature fluid vent, which was a little bit further out. And then we also we requested samples from a background site about 1 kilometer away, site 17. And you can see on the bottom image there a schematic diagram of sort of a cross section, which shows where these different sites are located. So we have this wonderful spread of samples from very close to pretty much at the foot of the main active hydrothermal site, all the way through to a background site. As this was obviously an IODP expedition with a lot of scientists taking part and producing lots of wonderful samples, there's already been some work done at this site. So I'm just going to briefly go over some important work that's pertinent to our study. So a study of sulfur isotopes in pyrite from within these rocks show an increasing incorporation of sedimentary sulfur away from the sulfide mound, as we see those magmatic sources from the chimney going through to the background site. A study that lasted over 12 years looked at the fluid sources coming into the system and found that they were homogeneous and also alkalic, which is consistent with there being a lot of terrigenous sediments actually at this site. More recent study by Yates et al. Came up with the idea that the background site there, the site 17, was a point of seawater recharge, and that seawater enters the system and flows laterally along faults and porous units to recharge the hydrothermal system. They also identified some very important alteration zones, which we'll come back to towards the end of the talk. So on the sulfide mound itself, there are massive sulfides with quartz and magnesium chlorite and also silicified volcanic rocks. As we move into the more background sites, we have magnesium chlorite and quartz alteration zones. There's kaolinite and cerussite zones quite close to the chimney. Illite, montmorillonite, a little bit further away. And then finally, some oxidized and completely unaltered lithologies as well. And it's important to note that in this particular study, we requested samples from all of these alteration zones, trying to get as close as possible to these same samples that were previously studied to add in some isotopic work. And these lithologies range from altered volcanic rocks, silicic volcanic rocks, all the way through to some clays. A little bit about the mineralogy of two of the key sites. So this is from the active sulfide mound, so lots of metals precipitating in this environment. You can see that the main mineral that we have here precipitating is sphalerite, which makes up the kind of the network of this particular sample. We also have some galena all the way through the sample, some pyrite with chalcopyrite on the edges of this mineral. And finally, we have anhydrite and gypsum filling in some important sort of pore spaces between these sulfides. So this is from site 13, which is a piece of chimney debris quite close to that mound. And we see some similar minerals. We have that sphalerite still as an important mineral. We have pyrite as isolated blebs. We have cerussite alteration, probably of the original volcanic rock. But importantly in this slide, we also have covellite, which seems to be a secondary replacement mineral. Putting this into a bit of a generalized system-wide mineralogy, and we can look at these in terms of relative time, but also relative decreasing fluid temperature. We start off with pyrite and chalcopyrite. We then have precipitation of sphalerite and also the galena, the lead sulfide. We have that replacement, that secondary mineralization of the covellite, which is a copper sulfide. And then finally, we have the anhydrite then being replaced by the hydrated form of anhydrite gypsum. So these importantly are in two categories. We have our reducing environment where we have the precipitation of our sulfides, and we have our oxidizing environment when we start to get that seawater coming in of the anhydrite and the gypsum. And important to note that you can see the image there of the Kuroko black ore. This site was previously labeled by Yates et al. As being an example of Kuroko black ore, which is a VHMS deposit. So to summarize that mineralogy, the copper-bearing minerals occur very early on, probably when we have the hotter fluid in the system, so things like chalcopyrite, or they do seem to crop up later as a replacement texture, as in the covellite. So we have reducing conditions, creating the sulfide precipitation, followed by oxidizing conditions once we get that seawater recharge. And that's consistent with previous work with that lateral flow of fluids and probably waning magmatic activity. So now Tom is going to take over and is going to talk to us about why we wanted to use chromium and strontium isotopes and what our data shows.
All right, thanks very much, Lucy. So as she's mentioned, I'm going to be talking about both the chromium and strontium isotopes. And to give a brief overview of them both, the main thing we know is they both have known, and in the case of chromium, unknown fractionation trends. So to start with the strontium isotopes, we know that they're sensitive to their source inputs and are unaffected by metal precipitation or redox. And what that means is that depending on their source, we can essentially use that as a proxy for how much mixing has occurred from starting at this end member of a magmatic source, as shown in the diagram, to a seawater source, moving from less radiogenic to more radiogenic. With the chromium isotopes, it's slightly more complicated in that we know they are redox sensitive with their mobility, and it's this redox sensitivity that is where they actually fractionate. What I mean by that is under oxidizing conditions, we can mobilize chromium in its chromium-6 form, whereas under reducing conditions, we get an immobile chromium-3. And as we know in this hydrothermal system, Luce has already pointed out in the mineralogy, we have both the oxidizing and reducing conditions. So with the chromium isotopes in general, we would initially expect an unfractionated chromium, unfractionated chromium be considered igneous silicate earth of 0 to negative 0.2 delta 53 chromium. If we were to have heavy values, we would consider that our seawater input. And if we had to then get negative values, we then consider that an anomaly. And as per a 2019 study from Bauer et al., they identified that on the distal flank of a hydrothermal system, they got these light values. So talking a bit more in detail about the chromium cycling, we have these two main inputs. If we start with our unfractionated igneous silicate chromium, being that chromium-3 and the immobile, we can oxidize that and weather it and mobilize it through the riverine system, and that is our dominant input into the ocean. And that is in that redox where we go from chromium-3 to chromium-6, and that's where we fractionate it and get these heavy values. And that accounts for approximately 90% of the seawater input for chromium. So that's the dominating seawater value. As for the unfractionated igneous silicate chromium, that chromium-3, that can also make its way back into the ocean through a detrital input. However, it can also be mobilized through acid dissolution. And important to note with this chromium-3, this acid dissolution doesn't actually fractionate or change it. It actually mobilizes chromium-3. It doesn't change it to chromium-6 at all. So it's not a redox reaction. Further to that, when we get these mixings, we then get this cloud around the vent itself. So whether the massive amounts of precipitation from a hydrothermal system, we then got what we call a partially reduced chromium-6, so where a partial from the seawater is collected by the metal precipitates, and in this case of chromium, we have a significant amount of iron 2 being the main factor that is able to capture chromium-6. And that reduces it and precipitates it onto the ocean floor. Now, this is on the distal flank of a hydrothermal system. That is where the anomalous value was found in the Bauer paper. However, that is still the footprint of this. That is the unknown that we're really trying to identify in this study. So what we were hoping to find of this is we thought that the further from the active chimney we went, the less dominant the magmatic or hydrothermal influence would be. And that would be identifiable mainly in our strontium isotope. However, we want to know is this isotopic signature predictable? So when we started our magmatic sort of source, are we going to then get more and more closer to our heavier seawater chromium? Are we going to remain unfractionated? Or as we get closer to the distal flank as identified by Bauer, are we going to get these light isotopic signatures? And if we do get these light isotopic signatures, where do we find those? So what we did actually find is that strontium is one of the major reservoirs for our gypsum and hydrate precipitation. And that what we have here is a plot of the concentration of strontium versus our calcium, a ratio of the calcium and sulfur. And we know that at a stoichiometric, we have a gypsum stoichiometric equivalence of just over 1, as the gypsum anhydrite chemical formula has an equivalence of calcium and sulfur. We know that anything that plots on that line is essentially going to be our pure gypsum anhydrite. So when we compare that with our strontium reservoir, we can see that that's our highest concentrations of strontium. If we were to then move beyond that, we would expect more calcium input into the system, and that would be likely due to increased seawater influence. And we can see, interestingly, our site 17 shows a significant amount above that, and that is likely due to the known carbonates that are precipitated in that area. So that's as we'd expect. Moving on the opposite direction, however, with an increased sulfur input, we would likely expect it to be a more hydrothermal input, influence from the increased sulfur from the hydrothermal system itself in the form of sulfides. And we can see that we actually have a nice trend that the closer we reach to this stoichiometric value, the increased strontium we have, and the more, and the further away from we are, the reduced. An interesting point to note of this is this could tell us that we have a mineralogical control on our fractionation, as our samples that we have come from a bulk sediment and have not undergone any leaching. So that's something that would need to be investigated further. However, what we do have, and what we did find looking at the chromium and strontium isotopes, we have our delta 53 chromium on our y-axis with our radiogenic strontium 87, 86 on the x, is that we actually had a fairly restricted strontium values, except for some extreme outliers on the far right there, as well as we had a large range of our chromium with both some extremely negative and positive values. We have a plot here. We've added to the plot the expected values for the seawater for the strontium 87, 86, and we can see that the chromium values fall within it. However, it is less radiogenic. Also, if we plot the unfractionated igneous delta 53 values, we can see that we do still have several values that fall within it, being our recently hydrothermal or distal alteration. But we do have, as well as our hydrothermal end member on the far left there, and this was a proposed hydrothermal end member from the Pacmanus back arc system by Roberts et al. In 2003. So the interesting thing we see with this is we have mixing trends that we can identify from the site 16, from the sulfide mound. So although we have several values that fall within range of the chromium and strontium sort of mixing lines that have been plotted on here, we can see that two values actually sit anomalously above that, and that kind of suggests to us that we have a mixing trend between them, as well as some other factor that is influencing the system. If we then look at the alteration zones that have been developed by Yates et al. In 2017, we can see that we have these values that fall within the unfractionated actually seem to sit with our near surface, unaltered or low temperature alteration zones. The heavier fractionation ones that were within a mineralization fluids of greater than 250 degrees. And our lighter fractionation ones were also deeper fluids at greater than 250 degree alteration zones. And what this kind of shows us is that our higher temperatures, whether it be deeper mineralizing fluids, that is where we seem to be getting our extreme fractionation. Whereas the lower temperature near surface kind of shows us that we have a less fractionation occurring within the chromium. Again, this could be as a result of mineralization, and further work need to be done to confirm this. However, we do have some interesting trends appearing that show that further work could be beneficial. So to summarize the concluding remarks on what we've covered today, so further work on the mineralogical control on both the chromium and strontium isotopes, and comparing those to other hydrothermal systems, would also say that more data would likely be needed for both of those, as we had a fairly limited data set for the chromium isotopes. The strontium 87, 86 was found to be fairly homogeneous, and the mixing between, and show mixing between magmatic and seawater source fluids. The other thing is that the sulfide footprint was very localized, and that the sites seemed to show small groupings of their own signatures that were completely localized to their vicinity and didn't seem to spread beyond their coring. However, we did have as I mentioned, distinct signatures of both heavy and light, and that their linkage to the active redox cycling of chromium in the area. And for further work, if we were to look at other redox-sensitive metal isotopes such as copper or zinc on the left there, this could assist us in providing additional constraints as they have a lower seawater reservoir.